So, remember, do you understand this? So we remove node A, and this link, and this link, and this link. We remove 3 links, 1 node. As a result, we have to add 2 shortcuts. That's how they purge the network. And for creating the hierarchy, we have to select which nodes to remove. So they compare 2 things. For each node, we can calculate one thing called edge difference, which will be equal to the number of added shortcuts deleted by the number of removed edges. So we want to remove the edge and at the same time remove the link, or remove the we want to remove the node and at the same time remove the link. So the more we can remove, the highest priority we have to remove that node, right? So for each node, we can get the edge difference, which is equal to the number of added shortcuts minus number of removed edges. And we have another measurement called uniformity. And this is equal to the deleted neighbors of this node. So we want to remove the nodes not only at one place, but evenly along the network. So if one node already has a lot of neighbors removed, we probably have to keep it. And the weight, and then we define something called the weight, which is equal to a constant multiplied by E and another constant multiplied by U. And we use this weight to sort all the links, or all the nodes. And then we bypass these nodes sequentially for every level. By bypassing these nodes, we can get a new layer or a new level. Understand? If we already created that, we can use this transit node routing strategy to quickly calculate the shortest path from A and B just using several table lookups. This is node from node S. There is an end node T. So let's assume we have only 2 layers, and S is in the base layer. And from S, if we do a shortest path search, we can quickly find several nodes that exist in the upper layer, the more abstracted layer. So these are called access nodes. Okay, so S is in lower L. Access nodes are in layer L1, L plus 1. Okay, so you find several paths. And for the destination, you can also do a shortest path query, and you will find several adjacent access nodes. And for each access node, we have a table that is recording the distance between these 2 pair of nodes. So we check, for example, for this node, for this access node, and this access node, we check a table. And in this table, we can find their distance, right? And this one, and this one, we can check their distance using this. So we perform a quick lookup in the tables, and then we can find the distance between these adjacent access nodes of S and these access nodes of T. And we apply a locality filter to see if S and T are in a local area. If not, you will be the distance from S to T will be equal to the closest one of these pairs. So S to this access point, then the access point to that access point, and the distance between this access point and the destination. And this is a local search. This is another local search. Between them, we can just use table lookups. So let me give you another question. For this case, this case, how many table lookups are there? So S has 5 access nodes. T has 6 access nodes. 6, right? So we have to perform 30 checks in this table. But this is very quick comparing to constructing a shortest path tree, right? Do you understand this?
So the distance, just the length between two nodes, not
Yes.
the length of the path between the...
It's the shortest path distance between these access points, which are already pre-compiled. So this entry means the access point here and the access point here, the distance between them on the shortest path. Do you understand this? Any question about that? Another thing I talk about is called the locality filter, and this is quite complex, so I don't need you to understand it. The locality filter means if we use locality filter and we find that S and T are kind of within a locality, then we just directly perform a shortest path search because they are close enough. And otherwise, we have to use these transit nodes or access nodes. I already listed the reference here on the blackboard so you wouldn't see, but when you go home, you can check this paper if you are interested in this. And I don't think I can explain this very well in this class. But I list them here. You don't need to understand this for any midterm or homework. Let me give you the example of Western Europe. Initially, they have 18 million nodes. Then finally they get only 11,000 transit nodes. And they have these number of secondary transit nodes. And they have this number of tertiary transit nodes. So the network is constructed into several layers. And in their result, 98.7% queries only involves a few table lookups. And for the local searches, they involve only several nodes, so they can be done very quickly. Do you remember the speed I said? 5 seconds for Dextra, but now it's 5 microseconds for global queries, and 20 microseconds for local queries. Local queries is using Dextra, so it's a bit longer. The global queries are only using the table lookups, so it's much quicker. To do this, they have to pre-compile or pre-compute some information. That takes less than 3 hours. And the pre-computing information takes 4.5 gigabytes. And that's why on your GPS, you have to store a lot of big files. I think those files are containing these shortest path information. That's my guess. I'm not 100% correct. And here, the part you cannot see is the paper. That's very important to transportation people because it's published on Science. So transportation papers are typically not published on Science, but this paper was published on Science in 2007. You can check this out, although it has only 1 page. Another thing I forgot to mention is here. Let me check out. Okay, let's skip. Sorry. So here in that paper, another paper, the author listed the chronicle of shortest path. As early as 1959, Dextra proposed the first shortest path that we are using until today. And the speed up, you can still have these fields. Pre-processing time 0. Speed up is 1. So we use Dextra as a baseline for comparing the speed ups. So if that's 1, then using transit node, was published on in 2006. Speed up is almost 1.4 million, and the most advanced one, the speed up is 3.3 million, and that's how our transportation, like shortest path problem, is solved. So for today's homework, I realized that last week I was giving you too much burden. And although I thought you can just simply follow my videos, but it's actually taking you too much time. So I apologize for this, but I think it's beneficial for you. I mean, you can submit that later. It's beneficial for you. I mean, in several years, you are going to forget what I taught you. But you can take a look at your own notes, and then you will easily recover what you have forgotten. For today's homework, I require you to concisely and accurately describe the dextrose aggregator using your own words. Don't give me any formula. You can use notation, but no formulas, no figures, no codes, no examples. So use your own language to describe dextrose. I know, I mean, for people like Jay, it will be very easy, but for some Chinese students, it will be very difficult. But I want to give you just a training. You can Google a lot of references, but I want to mention plagiarism, if found, will be handled very seriously. So don't just copy from somewhere else. Use your own language. After you understand other people saying, use your own language. This is already done in some papers. So they already use the illustrative or descriptive languages to describe this. Another thing I want to mention again, name your PDF files as first name number.ptf, and the first character of first name should be capitalized. Half of you, I don't know why they don't submit your files like this. Now it's the end of the lecture. Thank you.